Hello, thank you everybody for coming today to our 8th lecture. Today we're finally going to talk about the neural networks. Probably this is what everybody was looking for. Today we're going to see how one can motivate neural networks, how you can train neural networks, and what makes them so successful in the last years. So, to start, when you remember how logistic regression worked, we can actually organize that into kind of a graph, into a neural network already. And we can do it like this. We have our function, the sigmoidal function, at the end as before, as the output. And what we put in is a weighted sum of the features of our data point. Now, we can, as we've seen in the last lecture, augment this now with a kernel. Where our feature mapping gives us new or a different set of features calculated from the original data point that we had. And the output here is again sigmoidal function of a linear combination, and that is this times the weights multiplied in a scalar product multiplied with the features, with that the feature mapping phi yields. Now, this of course is still limited. But the choice of our feature mapping, and even as we discussed the last time, even if there are feature mappings which are infinite dimensional, which can, in theory, approximate everything, it doesn't mean that this is a very clever idea, because the representation might be very, very complicated. So what can we do? What we can try to do now is we can try to learn the feature mapping itself and come up with a very good and very effective and small feature mapping. And basically, we can keep our principal approach here and just substitute each of the leaf nodes here with a more complicated function that we can in turn learn. So instead of using the features or the feature mapping immediately of the features of our original data or the feature mapping, what we do is we calculate an output of what is basically a different logistic regression. And in this example here, we say, okay, we want to have 3 logistic regressions, and from their output, we calculate the actual prediction. And we can now extend this idea to ever more complicated architectures, basically just repeating. What you could also do is you can change the function here that we call the activation function of the neuron. One node in the graph is called a neuron. So in general, so if we extend this idea now, we have more more neurons, more of those logistic regressions, and we use them for even more logistic regressions, and only then, after repeated application of this, we calculate the final output. So we could call this here output layer. This would be the input layer. And those two in the middle would be 2 hidden layers. Now, we can arrange that in layers, because what we do is we feed forward the outputs. We get in something that we know, we put it into the first layer, we feed it forward, we calculate the outputs here, and the outputs are in turn used by the second layer, and they in turn are used then by the output layer. So in this sense, we're feeding through our data and the activations. So we call these things neurons, and each neuron, the output of each neuron the output of a neuron is then given as some activation function f. Here we have chosen, or I drew in a symbolized fashion, the sigmoidal function. And we could have, chosen any other activation function as well. And we take the a weighted sum of the output of the input neuron. So the Ni are basically the child nodes of, or the parent nodes if we go upwards, of neuron N. And the function f that we have used is the so-called activation function. I'll write that again. Why do we call it a neural network, or why do we call it a neuron at all? So there is a model of the human brain, or of biological, of brains in general, that the neurons in our brain are structured in a similar way, and that the activation of a biological neuron happens in a similar fashion. So if there are enough neurons firing activated that are connected to another neuron, then this neuron will become activated as well. And this is basically what we captured here. So you can get a threshold of when this gets close to, or is above the sigmoidal function output, something above 1/2, and then you say the neuron is activated. And it depends on the activation of the neurons before here. An important thing is that we are almost forced to take a nonlinear function for f, because if we use a linear function, that could be is actually similar to using the identity, and then all your hidden layers could be condensed into just one single layer. You can easily calculate that it basically comes down to each layer with a linear activation function is like a matrix multiplication. And several matrix multiplications can be done just can be condensed down to just one matrix multiplication. Therefore, the layers would be useless. So we need a non-linear activation function. Common activation functions are, one of them is the so-called rectified linear unit, ReLU, that gives you for a non-negative input, the input itself, and for negative values, just 0, and a leaky ReLU will give you for a negative input something like maybe 1/10 of the input, and still the input itself for the positive part. So it is non-linear because it is like hinged shape. We can maybe demonstrate that. So for the ReLU, it is 0 in the negative part and the identity for the positive part. And if you have a leaky rectified linear unit, what you do is basically you just tilt the output you tilt the graph for the negative part a little bit downwards so that you do not get 0. Why is it maybe preferable not to get 0? The problem is that the gradient, the optimization, kind of depends on the output that we have from the neuron. So, and if that output is always 0, and that might happen with the normal rectified linear unit, nothing will ever change for the neuron, and it's basically a dead weight that you have to carry through the network, and that has actually no influence on the training. Another one are the sigmoidal functions, like we've seen for logistic regression already. So of course we could have taken not just 2 hidden layers, but we could have taken only 1, we could have taken 3, we could have taken 5, or what is by now almost a common thing, we could have taken 50. It all depends on the problem we have at hand. So a question that of course arises is, with this setup, what can we learn? What kind of functions can we even approximate with that. So the first thing to notice is if we have two sigmoidal functions, we can construct something like a hump. Basically, we take one function that goes like this, and we subtract another one that goes like this. And I'm sorry, we subtract another one that activates a little bit later. And in the difference between the 2 points where it activates, where the two activate, we have this hump. So when we have such a hump, we can, again, by using many of these humps, we can approximate give any graph just by basically saying, so we have this graph here. And what we do is we use many of those humps to build that graph, and we just have to add them. So that means we can approximate actually any function arbitrarily well by making the humps very thin. So neural network and MLP with just one hidden layer can already approximate any arbitrary function. So we need this one hidden layer to construct the hump, and the output layer then makes the sum of all those humps. So the question is now, how useful is this, of course? How many neurons do we even need to construct something like that? Can we find the correct weights? Because to even construct a hump, we have to find a suitable choice of weights, right? To even make this hump, and then we have to arrange it in the correct way. So we need some automatic procedure to find the weights, and can we even do that? And finally, how will does such a neural network generalize? So the answer is we might need a lot of neurons. So it is very easy to find examples where you need exponentially many. It is also very hard to find the correct weights, and if we take a one-layer MLP, it usually does not generalize well, but rather it tends to memorize the data, so it tends to overfit. What can we offer as a solution here, at least for the many neurons? The solution is we go deep. We make the neural network deeper. For some functions, if we have a neural network with a few layers, to approximate them well, we need a large number of neurons. However, if we increase the number of layers, so one can analyze that for some functions, one can show that for those examples. If we increase the number of layers, the number of neurons collapses, and we only need very few neurons. So we can make more complicated function just by adding layers instead of adding neurons. And by using more layers, we can also reuse and share and build successively more complex features. And one of the most famous examples is now the neural networks that do the object recognition. So what they actually do is they, at the lowest stages, detect things like edges, very, very simple things, just colors. And out of the edges, in the higher layers, they build more complicated features. So you can actually make the face of a shape, the shape of a face. The shape of a face actually is very well detected by looking at basically lines. You have a line here with your mouth, and it separates a more complicated part of your face with a nose and with eyes from a part that is pretty much uniform. And you can look at a separator that goes along your nose and then looks for dark spots on a picture, usually to the left and to the right, which make your eyes. And by first being able to detect edges, or looking where you can find an edge, you can construct then things like combination of two edges, nose and mouth, and then you can look like things for maybe dark spots actually can also be thought of as combinations or of edges or intersections of edges, right? Like when two edges intersect, it's like a point, like your eyes, and with that, the neural network can construct something, a feature that captures the idea of a face or the general look in some way of a face. And this is only possible, this combination, this recombination and reuse of features is only possible if you have actual deeper topologies. So topology in the context of a neural network basically means how the graph that specifies the neural network, how that graph looks like. So this is an example how you could think of or how you can build more complicated features out of simple ones. So now, of course, the big question remains, how can we determine the weights? And with the weights, of course, also the features. So in general, there is no feasible way of finding the global optimum of the weights for your training, for your optimization problem that arises in training, and that is because the functions are highly non-convex, so they are very non-linear. Nothing there is convex, and it is full of local optima. So also think about all the symmetries that you have there. In the classic topology of the neural network, you can just switch two neurons and nothing and the corresponding weights, and the output will be exactly the same. It will be identical. However, you changed all the weights. So you have a lot of symmetries. Symmetries meaning that you can switch two variables and it has no effect on the problem. So you already know if you have some minimum, maybe some local minimum in some quadrant of your optimization problem, you will have similar minima, basically just in another quadrant, because all the quadrants behave, or many of the quadrants behave in a similar fashion. However, one thing that I want to note is that current research, I think it was either from 2018 or from 2020 even, indicates that if your network is only big enough, if it is broad enough, And if it is initialized in a certain way, then you know that all the local minima that you will find are actually global minima. So in some sense, it seems like even though the network has a very hard optimization problem in theory, practically, if you just make it big enough, the problem is actually not that hard. And it is a finding that you can verify for yourself if you try several, if you try a very big multi-layer perceptron with one hidden layer, and you and your friend both train it on the same data, you will find that the performance that they yield will be pretty much identical after training. And that is an indication that the differences in the optima actually do not seem to play very significant role. However, when you try the same experiment with a very small neural network, where your hidden layer might have only 2 neurons, then you will find that even among different runs, you and your friend, or you among different runs, will get vastly different performance. So from the non-convexity, if the network is not big enough, we don't really know what is coming out. So if you trained the neural network and the performance is bad, that might be because the training went wrong, but it might also be because the neural network is not able to provide better performance due to its topology, due to its activation functions, due to whatever. So there is in general, sadly, no guarantee. And the way we approach that then is we just do gradient descent to a maybe local optimum, and either make a very large network or ignore that we have no guarantees. And one question remains now. When we want to do gradient descent, we need to know the gradient of the error function with respect to the weights. And how can we calculate that? Maybe if you try to calculate analytically the gradient of a very complicated function, of a nested function, you will find that this is actually not that easy. And with very, very benign functions, if you combine them, the analytical gradient or the expression for the gradient will be very complicated. And for something very big like a neural network, where in practice you might have thousands of neurons with millions, over millions of weights, then this becomes infeasible. However, there's a trick, not even a trick, there's a clever way to calculate the gradient that is called backpropagation. and that allows you to pretty much just perform a bunch of matrix multiplications, and with that calculate the gradient of the weights of the error function with respect to the weights. By the way, this is also why nowadays GPUs are so famous for deep learning, because GPUs are specialized or are made in a way that they can do a lot of matrix multiplications. And this is exactly what you need to calculate the gradient. So to do one gradient update, one gradient descent step, you have to do all those matrix multiplications, and the GPU can do that quite fastly, in a very fast manner. So this is why the GPU became so famous in the deep learning applications. So now that we know how we can train the neural network, we might want to know, we might look for some ideas on how we can choose the topology, choose the connections between the neurons. Now, there are a few very common things, and some of you might have already heard about them. Things like convolutional neural network, CNN, or a recurrent neural network, or pooling layers. And what we're doing there is basically, instead of saying we have a fully connected layer, that means every neuron in the higher layer, except for the recurrent networks, every neuron in the higher layer is connected, has a weight for each neuron in the layer below. We now say, okay, actually, we only want some of the neurons to have a connection, and all the rest is actually zero. With that, we can reduce the number of weights quite dramatically. And we can also want that there is a reuse of weights. So let's look, let's write that down. Let's look at the convolutional neural network. So for the CNN, the idea stems from the classification of pictures. And in pictures, you have the setup that most of the pixels or pixels in the neighborhood, pixels that are close to each other, are highly correlated. So there's a spatial structure in the image. When you have straightforward vanilla multi-layer perceptron, then there is no connection in between two neighboring pixels. If you permutate all the pixels, if you rearrange everything, then the information that you actually have in a picture, it would get lost completely. And but the multi-layer perceptron, it wouldn't mind. For the multi-layer perceptron, there would be no change. So we can try to exploit the spatial structure, and this is what is called a convolutional neural network, because the operation that you say, I want some of the neurons to be only connected to the pixels in this region, is similar to convolution. So how might that work? If this is our image here, then a convolutional layer might work so that we say a square of 4 pixels makes the connection, or makes the input neurons for one in the next layer here. I use different colors just so that it is more easily readable, because now it can get very complicated here. So now this neuron here is responsible for things that happen in this square. This neuron here is responsible for the things that happen in this square, and so on. And when you have things like the edge feature, then what you can do is you look at all the different places in the picture, all the sub images, and you look if you can find the edge in this, or the combination of edges in the sub image. So this is why you use the convolutional layer, and it also allows to share weights, because you can make the same filter. It's called a filter. You can use the same set of weights for all neurons here, and you can just make a bunch of different sets of neurons, which again have their own set of weights. And with this, for example, this set of neurons could check for an horizontal edge, cutting the image in half, while the other set of neurons with the shared weight could check for a vertical edge. So each of those neurons would look if in the respective sub-image that they look at, there's the horizontal edge. And each of those would look at each of their sub-images, and again at each sub-image, and check if there's the vertical edge. And you can then combine that, for example, with pooling, which takes a bunch of, where you can take a bunch of closely neighboring neurons, and you can, for example, take the maximum of their activations. Why would you do that? It means if this neuron here detected the edge, but this didn't, then a pooling of this region would tell you, yeah, there is an edge. The pooling would say, it doesn't tell you where exactly the edge is, but it tells you that somewhere there was an edge. In this whole region, if there's at least one edge, then the pooling would be activated. Now you can also think of that in terms of in terms of object recognition. So if anywhere in your picture the neural network can find a chair, then via maximum pooling, in short max pooling, you might get an activation for chair, which only tells you, okay, somewhere in the image there is a chair. For example, if you want to avoid something, if there's danger, then it might not be that important where the bear in the image is, or where the danger in the image is. It's just enough to know that there is danger somewhere, and the corresponding output should be activated. So that is the idea of convolutional layer. And an important thing is, as I said, that we share weights here. This also means that we have something that is called an inductive bias. It means that we already preclude, we already assume, already put in the idea that the weights that have to be learned here are universal over the whole image, or are of importance over the whole image, and not just in a tiny fraction of the image. Because the multilayer perceptron has it treats everything equally. So for one layer multilayer perceptron, every neuron in your hidden layer looks at the complete image, and it doesn't matter if you shuffle anything, and it doesn't matter if you exchange two neurons. So both of them can have completely different features that they look at. And that means that basically you have a whole new set of degrees of freedom for each neuron. And that means that it is way easier for this topology to not pick up an actual pattern, but to suffer from a lack of training data. For recurrent neural networks, there is a flow in the network that goes backwards. So there's some kind of feedback loop. Now, how are you supposed to train that? Actually, what happens is that there's no real connection backwards in time or anything, but what happens is that the neural network is so-called unrolled in time. So let's say we make it a little bit, we can keep it like that. And at each time step, the edge does not go backwards, but it goes to the neuron in the next time step. And so on. Where would you use such a network? You can use it when you have a sequence of data. So natural language, speech is one of these examples. When somebody gives you a sentence, somebody talks about something, and you get a continuous stream, not continuous, but you get a stream of inputs of one word after another word, and so on. And maybe you want your neural network to be able to pick up on such a stream, and then while listening to the stream, decide what the stream is about, and not having to look at the entirety of the stream at once and then decide. So that might be something of interest, right? Also, when you have a time series, you can in some sense consider actually language as a time series. When you have a time series, it works in a similar fashion, or it would be of similar interest. Now, one problem that you get is here, the weights are fixed here, so the weights here are also shared. And it means that if the weight is smaller than 1 in the repeated matrix multiplication, we will get a smaller and smaller with each iteration, with each temporal layer gradient. So it will vanish. If it is, however, bigger than 1, we will multiply that part over and over with something that is greater than 1, and that means it will go exponentially, increase exponentially. So for recurrent neural networks, it is very easy to get a vanishing or exploding gradient. And there are several topologies that try to fix that. For example, the what's it called? The long short-term memory, LSTM, which basically says that the recurrent edges are fixed to 1. So it makes a specific part of the architecture that is, which task is to do the memory, to keep the memory. And in this memory, where you have the feedback loop, the weights are fixed to 1 so that there's no exploding or vanishing gradient there. So we talked about recurrent neural networks, short introduction to convolutional neural networks. Of course, all of these things are so huge by now that it's impossible to talk about it in a justifying manner in one lecture. Also, neural networks are really more of an art than a science, in the sense that there's a lot of trying involved. It is more an engineering feat. You have to come up with the right topology. You have to tweak everything in a way that it works, which is largely a process until today of trial and error. So usually there's no special way of making the neural network, and the neural network will solve the issue, which is a stark contrast to, for example, linear regression, where you know exactly about the quality of your solution, where you know exactly about its performance, its variance, its bias, and all those things that are otherwise completely unknown here for neural networks. So this lecture is just meant to give you some idea, so that you've heard some of the most important punch words, and when you read something online, that you might have an idea what it's roughly about. So we've talked about the convolutional neural networks, we've talked about the recurrent neural networks. You can also include in the topology something that is called a normalization layer, which basically all it does, it doesn't really get trained, but what it does, it scales the norm of its input to 1. So if over the course of your network, the input gets smaller and smaller and smaller, which might happen, and the network can become quite oblivious to that, because it just deals with relative activations, right? So the network, but this layer can rescale it so that the total norm of the input is 1. It also allows you to treat the different batches of different sizes as if they had the same size, but were maybe more but they were more precise. We've talked about the pooling layers. We've talked about the shared weights. So the shared weights are an incredibly important factor of modern day neural networks. Can't emphasize that enough. So applications are, of course, there's of course an extreme variety of applications. So I'm keeping it more abstract here. On supervised tasks, that means where we already know the label, you can use them for regression problems, and for classification problems. Unsupervised basically means you give the network a bunch of data, or the data set that you have, and you want the network to extract, for example, important features, or make it learn the distribution and things like that. So there's no real label involved here. It's just data, and the network has to do something with it. Has to find something interesting in the data. There's something that is called an autoencoder. An autoencoder is similar to a regression problem, where the network is supposed to map the input to itself, but via a special encoding. So you force the network not just to take the identity to output what it was put in, but to find some embedding, some representation of the input, and from that representation, it has to reconstruct how the input looked like. So you can use that for dimensionality reduction. Basically, you have something like that: in, out, and hidden. And the hidden layer is way smaller, or the hidden layers basically have a bottleneck, where they force a compression. And from the hidden representation, the autoencoder has to reconstruct the output. There are so-called generative adversarial networks, GAN, generative adversarial networks. And what they do is basically they are learning the distribution. However, how it works exactly is a little bit too complicated for to dive into now. On a high level, we have two networks. One of them tries to generate a sample, and the other network tries to tell apart, or tries to tell if what is generated is actually part of the distribution that is in question. And for learning, or for doing the training, there's a random initialization of the weights. people can augment the data set. Though this is something that works for most machine learning things, most machine learning applications. So you can, if you have pictures, you can rotate them, you can shift them a bit, you can add noise to them, you can change the lighting in images. One can use dropout, which is a very specific thing for neural networks, where in each learning pass, the algorithm forgets about a share of neurons. So basically, you treat the neurons as if they didn't exist. You can say you can use a dropout rate of 50%. And in a learning pass, it will just set the activation of those neurons to 0, which means basically they don't exist. And then the training happens on the remaining neurons. So with that, it is as if there were different topologies. So every time you choose which neurons to leave out, you choose a specific topology actually. And among all those topologies, the weights are shared. So this is also a form of weight sharing and allows for way better generalization. And an important thing, of course, for the training is also to choose the right learning rate and the right or the best for the task suitable gradient descent algorithm. So as a recap, neural networks are non-convex, meaning usually the outcome of the training process is not guaranteed. They usually have high variance because we know that they have pretty much no bias. If it's big enough, you can approximate every function. And they can make use of feature extraction and feature combination. And this last point is really what makes neural networks so successful, because it allows them to adjust to very otherwise extremely complicated things. The real advent now that we have with image classification just comes from really deep neural networks, where people found out a clever way to extract features in a better and better and better fashion. So if they have a neural network with 50 layers, usually 45 of those layers are just convolutions, dropouts, normalization, stuff like that, pooling layers, where there's a lot of sharing between the weights going on, and only the last layers and the last layers then, and only them, have basically are fully connected layers again, which then construct the output out of this entirety of the feature set that the network generates. And last but not least, I want to give you a formula for deep learning. Which means the training of deep neural networks. So deep learning is the combination of having a lot of data, using stochastic gradient descent, which is computationally way more efficient than the normal gradient descent, reusing weights in the network, which gives you the inductive bias and reduces the number of parameters significantly. So just to give you an idea, if you have 2 consecutive layers where the first layer has n neurons, the second one has m neurons, and there's a fully connected layer, you have m times n weights that you have to adjust. And that number can be really huge when you have a pixel with, let's say, 4,000. An image with, let's say, 4,000 pixels, and all of a sudden you might have something like 4,000 times 1,000, 4 million weights just for one single layer. And if you do the trick with the convolution, you have number of filters, which means number of sets of shared weights, times sub-image size, which is way smaller. So if the sub-image has 100 pixels, and then all of a sudden you can make 1,000 filters, 1,000 features that you look for in each part, and you only get 100,000 weights that you introduce. And the last one is you need many layers, because you need to recombine the features. You have to find the features, you have to extract those complicated structures in the data. And this is what makes the neural networks nowadays so successful. So thank you very much for attending today. This was our second last lecture. So the next time we will look at dimensionality reduction and a bit of clustering. And I hope then that you got a little overview now today over the neural networks. So thank you very much, and see you next time.